Good afternoon. I am Krishna Kumar from Krishna's classroom. We continue with our talk on analysis on Rn. This is the 10th section. And before I embark on the discussion of derivatives of functions from Rn to Rn, we make certain remarks. Now the remarks are pertaining to the norms in Rn. Now you recall that we looked at the normed linear space. Rn with the Euclidean norm. That is the standard distance notion that you have in R. That is norm of x. I put 2 there equal to sigma and it comes out of x dot x, that is the dot product, sigma I equal to 1 to n xi x dot y yi, where of course x is defined as x1, x2, etc. xn. Y is defined as y1, y2, etc. Both vectors in R. Now this gives what you call a dot product, or later on we will introduce what is called the inner product, and then this is a standard inner product, and you can easily see that the norm 2 of x is essentially x dot x, that is that's a connection between the inner product and this, and we have already seen that this is equal to, one talks about the length of the vector, the other one talks about the angle between two vectors. Okay, so this is in R2 or R3. X dot y equal to norm x cos theta, where theta is the angle between two vectors, x and y. So something like this. Suppose this is the vector x, this is the vector y. X dot y is this. And that's a measure of the angle between the two vectors in the space. So it endows the space with a notion of length of a vector and also the angle between two given vectors. And in fact it gives you a distance notion, ρ2 of here. One thing that you should observe is that because we are in a linear space, x minus y is well defined, and it's a vector in Rn, and therefore its norm 2 is well defined, and that norm 2 is defined as rho 2 of xy, or this 2, the significance of 2 will be clear soon. Okay, and this is this. Okay, right. Now it comes from this particular 2 that is sitting here, or the 2 that is sitting here, and so on. Now what I wanted to say is this. Now we also have a look at this. Now this gives in R2, for instance. If you have a vector x, you have a vector y, then this particular distance is rho. That is the distance between these 2 points. That is the point P and the point Q, say. So distance P2. This is what it is. That's the direct distance between those 2 points. In fact, you have the analogous thing that you have in Rn also, you can define. Now what I want to say is this, that this is not the only distance notion that you can introduce in this. In fact, one can do the following. You can define, see, the distance notion has the following properties. What is the distance notion? This is what you call the metric, and we have already defined what metric is. Metrics, the distance between 2 points is non-negative. The second point is that it's equal to 0 if and only if the 2 points are identical. That means x equal to y. And then the third notion is that it is symmetric, that is rho of xy equal to rho of yx. And then of course the triangular inequality, rho of xy is less than or equal to rho of xz plus rho of zy. These 4 conditions are satisfied. And you know that rho is essentially a map from x cross x or Rn cross Rn to R with these properties. Then you say it is a metric space. And once you have a metric, you have the notion of what are called open sets, closed sets, and topological concepts are there. You can talk about convergence of sequences. You can talk about the continuity of functions based on that, and so on. Okay. So the norm or the distance function is here induced by the norm. Because of the linear structure, you can talk about norm. And norm itself, you look at what are the properties of the norm. Norm is norm of x is greater than or equal to 0. Norm of x equal to 0 if and only if x equal to 0. Norm of alpha x equal to mod alpha into norm x. Then norm of x plus y is less than or equal to norm of x plus norm of y. Now we have seen that in the case of Euclidean norm. So what this says is that this is defined for every x on the linear space, and it's a function from, suppose if x is the linear space, so norm is essentially a map from x to R. Norm is it is defined for each x and with the set of properties. Okay. So you know that there is the linear space operations, or two operations are there. One is addition and the other one is scalar multiplication. And you are saying how x plus y is mapped, or how norm of x plus y is related to norm of x and norm of y. Here how norm of alpha x is related to norm of x and alpha. So this is described. If you have such a function, then you call it a norm. Now the important thing that you should observe is that on Rn you can introduce several functions of this kind, not just the norm 2 function. For instance, let us look at R2. In R2 you take x, and x is defined as x1 ordered pair. Now we define norm 1 of x by mod x1 plus mod x2. This is the definition. Now is this a norm? That's the first thing that you have to observe. Trivially, norm of x is greater than or equal to 0 by definition, and norm of x or norm 1 of x means it is mod x1 equal to 0, mod x2 equal to 0. And for real numbers, mod x1 equal to 0, mod x2 equal to 0 implies x1 equal to 0, x2 equal to 0. In other words, x is equal to the vector 0, 0. So this is satisfied, and you can easily show that this is if and only if. The second one is norm of alpha x equal to, what is alpha x? Alpha x is equal to alpha x1 alpha x2. So norm 1 of alpha x is equal to modulus of alpha x1 plus modulus of alpha x2, or in other words, it is equal to modulus of alpha into modulus of x1 plus modulus of alpha into modulus of x2. So it's equal to mod alpha into, so this is easily verified, that is mod alpha x1 equal to mod alpha into modulus of x1 plus modulus of x2, that's equal to mod alpha into norm 1 of x. That is true. Now comes this one, and that's equal to norm of x plus y. This is equal to norm of, what is x plus y? X plus y is by definition it is x1 plus y1 this is, by definition, this is equal to modulus of now use triangular inequality for real numbers. This is less than or equal to mod x1 plus mod y1 plus mod x2 plus mod y2, and that is equal to mod x1 plus mod x2 and that's equal to norm x1 plus norm x. Now in this case you would have observed that the computation is particularly simple, unlike in the Euclidean norm, because there you have to use two inequalities, beautiful ones. One is of course the Cauchy-Schwarz inequality, which amounted to saying that mod cos theta is less than or equal to 1. Oh, that's all. That's what you had to use. But you have to use that to prove this. You compare the proof of this with the proof of the other. But this is also a norm. This is also a norm, and we would like to see exactly what exactly is the norm of a vector in this case. In this case, suppose you take a vector x1, x2 in R2. Then the length of this vector is essentially the following. That is, this is the length of mod x1, and this height is x2. Therefore, this is equal to the distance from 0, 0 to the point x1, 0 plus the distance of from x1, 0 to x1. Okay. So this is so this is actually mod x1 plus mod x2 that we have. Okay. So it is not the direct distance that you are used to calling a distance, and you can easily see that this norm satisfies all the requirements of a norm, and therefore from which you can easily prove that it is an inner product. Sorry, not an inner product. It endows a space with a distance you call ρ1. I leave it to you to prove this. And this is the distance. So it becomes a metric space. So there is a possibility that in Rn, what is the analog of this? Rn, the analog of the norm is this. You call this norm of x1 equal to sigma I equal to 1 to n mod x, where x is equal to so this is an alternative way in which you can make the space a normed linear space. Okay, but this one is called the Euclidean norm. This is not called the Euclidean. Okay. But possibly sometimes the computation becomes very simple. Another norm that you can define on this space. So as I said, this is the geometry. Okay. Another norm that you can define, let me designate it by norm infinity. This is equal to maximum of mod x1 mod x2 I can use maximum here because there are only finitely many numbers. So you take the mod x1, mod x2, etc., mod xn. and see what exactly is the maximum of this. Okay, that will give the distance. Once again, you can easily verify that. It's a good exercise. Show that. Norm infinity and hence rho infinity defined by now this is easily put. It's not difficult at all. Once you prove that it's a norm, it is very easy to show that this is a metric. Because in general, you know that norm of it is the norm of this, and you know that is certainly greater than or equal to 0, and rho of xy is equal to rho of yx. These are the properties. That rho of xy, which is defined is greater than or equal to 0. This is what you have to do. The rho of xy equal to 0 if and only if x equal to y. Then rho of xy equal to rho of yx, and rho of xy is less than or equal to rho of xz plus rho of z. This is what you have to prove. I mean, that's quite simple for both norm 1 and norm infinity. It's fairly simple to prove that it's a norm, and you know that once you define the norm and prove that something is a norm, it's very easy to show that it endows the space, the linear space with a metric by defining rho of xy equal to, this is the definition, whatever be the norm of x. This is the definition, and it gives you a metric space. Therefore, the same Rn can be made into different metric spaces by introducing a norm. More generally, so I will not go into the details of that, because that's a bit more difficult to prove. I just indicate what all things will have to be proved. That's all. Okay. Now on Rn, you define the following. We define norm x p to be sigma mod xi to the power p, I running from 1 to for 1 infinity, and norm infinity you define your value. Okay, so the problem here is that to prove it's a metric, sorry, it's a norm. So like the case p equal to 2, we need some kind of a extra tool to prove this. Okay. Now you see that what are things you will have to prove? You will have to prove this. That's pretty simple. And norm of x p equal to 0 and vice versa. So that is pretty straightforward for this. There is no difficulty at all, just from the definition it follows. So this is okay. 2, this is also okay. That means norm of that is also straightforward, because what you would have is you are getting alpha xi everywhere here, and you can write it as mod alpha into mod xi and to the power p to the power 1 by p, and you see that mod alpha to the power p can be pulled out, and then you are taking to the power 1 by p, so that will give you mod alpha and the rest will follow. That's straightforward. Okay. The third one is the difficult one. This needs a little bit of work. As you have seen that with p equal to 2, you had difficulties. It was not like the two cases that we considered, the two extreme cases that we considered, the case when p equal to 1 and possibly p equal to, it's not exactly p putting p equal to infinity, but that's an notation. Okay, right. So in both those cases, it was pretty straightforward to prove this. But here you need some work. In fact, you need the analog or the generalization of the Cauchy-Schwarz inequality. Okay? And use that to prove the case of the norm. And in fact, see, once p is given, p satisfies this, given infinity, there exists q such that this is a sort of conjugate number that you have for this. Okay. As you see, when p equal to 2, q becomes 2. Okay. There's a sort of dual number that you have connection. Okay. But when p is equal to 1, then q becomes infinite. When p equal to infinite, q will become 1, and so on. And this kind of connection is there. Apart from that, when p belongs to This is the connection. Okay. And for these two numbers P and Q, they play a very crucial role in the structure of the space and its dual space and so on. So that I will not elaborate at this stage. Later on, when you work with these spaces, you will know precisely what exactly they mean. What one can prove is this sigma xi yi is less than or equal to sigma mod xi to the power p mod q for P and Q chosen like this. Once P is given, then Q is fixed corresponding. So that 1 by P plus this condition is satisfied. And this is the analog of Cauchy-Schwarz inequality. And you can easily check that when P equal to 2, this simply gives the Cauchy-Schwarz inequality. So it's a generalization of that. Okay? And once you have this, then you can prove that. Then using this, prove that norm of P is less than or equal to this is called the Holder's inequality, and this is called the Inco Scheme inequality. So this is quite easy to prove. In fact, a more general result will be something like this. You have got a sequence of real numbers xn, that is xi, I running from 1 to n. Then you have got, and yi is another sequence, say y1, y2, etc., yn, real numbers. Then for that, this particular inequality is true. Okay? And then using that, one can prove this result. And that is quite, a small work, more work than, not straightforward like this. But first you would have to prove this inequality. This is called the Holder's inequality. Called Holder's inequality. This part and this part, this is what is called an Inco Scheme inequality. So you prove these two things using this. I mean, you can easily do that, and this needs some work. And once you get that, then this can be done without much. In fact, it is the generalization of Cauchy-Schwarz inequality, from which you prove the triangular inequality for now. So the triangular inequality is now a consequence of these inequalities. So the moral of the story is that there are several ways in which one can introduce a norm suiting your circumstances. But on a finite dimensional vector space like Rn, you see, there is a beautiful result which says that on Rn, all these norms are equivalent. So what do you mean by that? You say that two norms are equivalent, say definition. Two norms, say norm and norm star are equivalent. On Rn, if there exists positive constants A and B such that norm x, A times norm x is less than or equal to star norm of x if both A and B are positive. In fact, one can prove that all these norms this is something that you can easily prove. On this, I mean, it needs some work. You take the specific norm and then compute the corresponding A and B. But what exactly is the consequence of this? This is something that you have to observe. One thing is that the topological properties remain invariant whether you use the metric derived from norm or norm star. Okay? So the consequence is that all topological properties invariant. That means, for instance, you can show that given V2 let me put this also, just P1 and P2 could be infinity also. That is the meaning of that. Okay. then you see that norm of P1 where A and B are for some constants A, A positive and B positive. This is something that we okay. Therefore, for instance, you talk about something that you will have to work with is, say, convergence. If you have a sequence, if this condition is satisfied, then it is easy to see that if a sequence xn converges in the norm P1, then it also converges in norm P2. Okay, that's quite easy to see from here. In fact, you see that you can see from this part of the inequality, you will get 1 by b norm x P2 is less than or equal to norm x P1. Similarly, from this inequality, it follows that norm x P1 is less than or equal to 1 by P1 norm x P2. Therefore, you can write here 1 by b norm x P2 is less than or equal to norm x P1 is less than or equal to 1 by a norm x P2. Okay, so that's they are interchangeable with the appropriate constants interchange. So if a sequence is convergent in one norm, then it is convergent in another norm. Therefore, if a function defined on the space is continuous in one norm, then it is also continuous in another norm. Therefore, all norms are equivalent. So that makes that gives an advantage. When you check the topological properties, you can use the most convenient norm in which you can work. Okay. Now you see that this. Let me just look at the consequence of this norm. Something about the if you go to R2 and have a look at it, you get the unit ball determined under these norms, which is very nice to see the structure, and this gives you the kind of geometry that it endows the space with. Okay, let us take R. Now you see that, let us take norm 2. And what is the unit ball? See, B 2 0. So you define it as what is the unit? 0 is the center, and this is a 2 norm that you are using, and that is the notation. Okay, so you see that what is the unit? So this gives the disk this is, see that this distance is equal to this is equal to 1. Okay, so this is 1 0 0 1, so 0 1 minus 1 0 and 0 minus 1. These are the 4 points, and this is the point 0 0. But what about the other norms? Suppose you take norm 1. Then the corresponding such that norm of x1 is less than, I am talking about open form. So this is the interior. Okay. So that gives the condition that mod x1 plus mod x2 is less than. So if you consider the first quadrant, you will see that this becomes both x1 and x2 are positive, therefore you have non-negative, and therefore mod x1 plus mod x2 is less than 1 is essentially x1 plus x2 less than 1. And what is that? That is this line. Okay. Then you have in the other quadrants you can, because in this quadrant you see that x1 is negative, x2 is positive, and so on. So you get this, the picture of the unit ball coming out of this. So this is the picture of the unit ball. Okay, this is the one corresponding to P equal to 1. This is the one corresponding to P equal to 2. What about so you have B1, B infinity 0, x belonging to R2, for which norm of x infinity is less than 1, and that leads to maximum of mod x1 mod x2 is less than 1. Therefore, in the first quadrant it is going to be maximum of x1 and x2, that should be less than 1. Okay. So if it is x1, then you see the boundary is going to be x1 equal to 1. If it is x2, then it is going to be x2 equal to 1. So you see that this is the part that will come out. And then on this part it will be this, here it will be this. So this is the shape of the unit ball. This is now one can see that if 1 less than p less than infinity, then you see that so this is when p equal to infinity, this is the boundary of the unit ball when p equal to 1, and all others are going to be in between. Therefore, the shape of the unit circle or the unit disk is going to be this. This is -1, 0. This is 1, 0. This is now you see that the extreme cases are, this is p equal to 1, and then you have for p equal to infinity, this is corresponding to p equal to Now the circle P equal to 2 lies in between. This is the what you call the unit circle is a perfect circle. That's the case when P equal to 2. Now you can see that all of this are lying between these two lines. Okay. And when P lies between 1 and 2, when P lies between 1 and 2, the unit circle is something like this. Okay. And then when P lies between 2 and infinity, it is going to be something like this. So you see that when P lies between 1 and 2, it is this one. This is the shape of the unit ball, because it corresponds to mod x1 to the power p, mod x2 to the power p. So this is the circle that you have, and when p equal to infinity, p lies between 2 and infinity, this is what you get. This is the case of p equal to 2. So this is what you have. The picture is clear. You see that the picture is this. This is the case where p equal to 2, and the blue one is p equal to 2, and the yellow one corresponds to p lying between 2 and infinity, and this orange one is the one that lies between 1 and 2. So this is the case for 1. This is corresponding to infinity. This corresponds to 1. And this corresponds to the case 1 less than 2 less than infinity. And blue one is 2. And these are, of course, the yellow one corresponds to p lying between 2 and infinity. Okay, so this is the shape of the unit ball in R2 when you use different p's. And I think that's a good thing that you should observe. However, as far as we are concerned, it doesn't matter which norm you use. So you use the one that is computationally, at least while discussing the topological properties, it is immaterial in which norm to work, because all norms are equivalent, and that's the beauty. Therefore, you use the computationally simple norm for your work. That is the suggestion that you have. Okay. But Euclidean norm has a speciality. There are some special features of it. The Euclidean norm is somewhat special because you see that in that case p equal to q equal to 2. Whereas when p is some other number, q is going to be different. And this has got something to do structurally. As you have seen, it is also reflected when you generalize the Schwarz inequality. When you write the Schwarz inequality, both the factors have to the power of p to the power 1 by p. To the power of 2 to the power 1 by 2. Whereas on the right hand side you have two factors. One is sigma mod xi to the power p, the whole thing to the power 1 by p, multiplied by mod sigma mod xi mod yi to the power q to the power 1 by p. Okay, so you see that the dual nature of p and q is very significant, which merges in the case of p equal to 2, that is the Euclidean norm case. But Euclidean norm case is somewhat difficult for computation sometimes, whereas this is not. Okay, so that's the advantage that you have on this place, so that you can work. So I think I will stop here and then go to the concept of derivative in my next talk. So this somewhat concludes the structure of Rn as much as we require for our understanding, and this is a bit extra that I have chosen to give at this stage. Okay, please note that the equivalence of norms is not in general valid in infinite dimensional spaces, but we shall not discuss it here. So thank you very much.